Hey, BC Calculus, Mr. Ellinger here, and we're just doing a little video on sequences and series, kind of doing a quick going over of what you would learn in honors pre-calculus. So a very short version of that. It might be like a 2 to 3 week unit there. Here it's going to be a couple of videos, but we'll just focus on the stuff that you need to know for this class. Let's do it. So what's the difference between a sequence and a series? A sequence is just an ordered list of numbers. It could be anything. Here's an example: 8, 6, 7, 5, 3, 0, 9, and then 28, 36, 57, 44, 56. You might be wondering what those are. Those were the alphabetically first numbers on the Seahawks roster as of like 2 days ago. It's like a sequence is just a list of numbers, and there can be a pattern to it, and there doesn't have to be a pattern to it either. Generally, they're infinitely long, but you can choose to look at a portion, but we generally think of them as being infinitely long. The terms in a sequence are written A1 for the first term, A2 for the second, and so on. AN is the nth term, like sort of like any given term, like as sort of like as a variable. And so A1 in this case is 8, and A2 is 6. And note how the 1 refers to its place in the sequence, but A1 refers to the term itself. So N equals 1, but A1 equals 8. Hope that makes sense. So the A is the actual term. Right? And then you learn about some special sequences. So one is arithmetic sequence. You learn that. And the formula, having a formula for a sequence allows you to generate the terms. So I can plug in 1. I can say A1, well, N is 1, so I'll plug in 1 into the formula, and I get 6. And I could plug in 2 in, and I get 11, and I can plug in 3 in, and you go, I know what's going on here. You can see what an arithmetic sequence is. It goes up by a common amount. But these aren't really important for our calculus class. Much more interesting is one like this. It's called a geometric sequence. And a geometric sequence, well, let's generate the terms again. So n equals 1, so we put it in and we get 6. N equals 2, plug it in and you get 3. And then 1.5, please write, and then 0.75. And so a geometric sequence is one that has a common ratio. Please write for me, thank you. Common ratio between the terms. Now you might be a little confused because ratio, like, is the ratio 6 over 3 or is it 3 over 6? If we just say a ratio between terms, it's not clear. And so you always want to think of the ratio as what you multiply by to get to the next term. So, we multiply by 1/2, and so that's what the, times R. That's what the ratio is. So R is 1/2 in this case. Okay. R equals the ratio. Seems like today, if I write too quickly, then OneNote kind of goes, whoa, you're going too fast for me. And I need to rewrite stuff. And did I freeze it? 1 second. Okay, I think I got it back. So R is the ratio. I just have to make sure I don't write too fast, because if I write too fast, then OneNote kind of freaks out. Take my time. Okay, so sometimes you'll see a geometric sequence look like this, and so the example we just had was a geometric sequence, but sometimes it can also look like this, where the exponent is n minus 1. That's okay. What's important isn't the formula, it's the common ratio. So the formula could look really weird, but as long as there's the common ratio, it's okay. Like in this case, if I use this one, if I plug n equals 1 into this one, the first term I'd get is 4, because I'd have an exponent of 0. And then the second one would be 3/2 of that, which is 3/2 of that, which is 6. And then the next one is 3/2 times that, which is 18 divided by 2, which is 9, I think. And then so on. And so that one is one that's growing. That's okay. As long as it's got a common ratio, it's geometric. But if the terms are approaching a specific number, we say that the sequence converges to that number. This term converge is going to be used a lot this chapter. In calculus terms, let me move up and let me blow it up. In calculus terms, we'd say a sequence converges if and only if the limit, there we go, limit as n goes to infinity of an equals some number L. Right? So notice it's not the n, so the number of the term is going to infinity, but the terms themselves are getting closer to a number. That's what That's what will tell you if a sequence converges, is if the limit approaches something. If not, it diverges. So in the examples we just saw, looking at these two, an converges because we saw the terms getting smaller and smaller, and it would be half as big and half as big and half as big. And so it would converge to, sorry, getting my pen back. Okay, OneNote's freaking out on me, so I've switched to the Word file. We'll give that a try instead. So the sequences above, an converges because it's half as big, half as big, half as big. It gets closer and closer to 0. Bn diverges because the numbers just keep growing bigger and bigger and bigger, and they just kind of blow up. All right, some calculus stuff applies to sequences. So does this series converge? What do you think? Does that series converge? It's kind of a tricky one. You could plug in 1, you could plug in 2, you could plug in 3 and try to figure it out. Or we could say, well, what's the limit of this thing as n goes to infinity? I'm sorry, those should have been n's and not x's. Just notice that. Whoops, let me get that right. Of n to the 4th over e to the n. There we go. And so what would be that limit? And if you weren't sure, keep in mind that you could use L'Hopital's rule on this, right? Because you've got it's infinity over infinity, and that's that's a boy, I'm forgetting the word right now, but that's a unclear case. What's the word for that? Just totally forgetting it. But that's a situation where you can infinity over infinity. You can take the derivative of the top, derivative of the bottom, and you do it again and again and again, and you eventually find that it's 0. So therefore, yes, that limit that series sequence converges. There's also a squeeze theorem for sequences. So given that an of 1 over n converges, show that bn of sine n over n converges. And so remember, the squeeze theorem is when we have two functions that are approaching a limit, and if they're approaching a limit, then anything that stays between them also has to approach that same limit at that same value wherever you are. So we know an converges. That'd be 1 over 1, 1 over 2, 1 over 3. It gets closer to 0. And so I could say that converges. I can also say an equals 0 converges, right? Because that's got to converge because it's just 0, 0, 0, 0, 0. It's infinitely close to 0. And so this thing has to converge because sine n absolute value, just to take care of any negative worries, over n is always between 0 and 1 over n, because sine n is always going to be like a decimal, or at most 1. And so therefore sine n over n has to converge also. And just a little calculus moment there, just a chance to review the idea of the squeeze theorem. And then there's a little vocab here. A sequence is bounded above if you know there's a number that it can't get up to. So for example, this sequence that we saw right here, it's bounded by 12 because it can never go past 12. Right? It's never going to get bigger than 12. Remember, n on these is always going to start with 1, 2, 3, 4. You can't put negative numbers in for a sequence. It's got to start with 1. And so it's bounded above if you can just say there's a bound and it can't go above this number. And it's also bounded below. If something can be bounded below, like that one is bounded below by 0. And if it's bounded on both sides, you can just call it bounded. That means bounded both ways. Kind of like a limit. You can say a limit from the left, you can say a limit from the right, or you can just say it has a limit. And a sequence is monotonic if the terms never change direction, meaning like each term is progressively larger or each term is progressively smaller, one or the other. So an example of a theorem is if an is both bounded and monotonic, then what? So let's think about what this means. This means we've got some sequence that is giving value. So the y value here is just the an, and the x value is the n. You could put it on a graph if you want to, but that's the idea of this. So the first term, the second term, but wait, hold on a second. It's monotonic, so it has to, given that I've went up initially, it has to keep going up. So it's going to keep going up. It could stay the same for a moment, but it has to keep going up, or stay the same, or keep going up, or stay the same. But wait a minute, it's also bounded, meaning there's a top limit. There's some number that it can't possibly go past. Try that again. There we go. And so since it can't go past this, but it has to keep increasing, you realize like it's got to converge to something. Like it could stop right here, but then it's converging to that. If it keeps going up, then it's going to converge to something else, or it might converge to this. Maybe it'll converge to the bound that we've got right there. So if a sequence is both bounded and monotonic, then it converges. That's an example of the kind of sort of logical conclusion you can make about sequences. Okay, it's a good place to switch to the second video, so I'm going to do that, and then we'll talk about series in the next one. Okay? Thanks for the technology patience.